Hello, I'm Roman, and welcome back to the series of videos Neural Networks from Scratch in Golang, where we implementing neural networks from scratch in Golang. And to do this, we're using this book called Neural Networks from Scratch in Python, but as you can already guess from the name of the series, we're using Golang. And in the previous video, I almost finished with the chapter 9 of the backpropagation, and we implemented this combined activation softmax loss category cross entropy loss class, which basically calculates the backward method for softmax and category cross entropy loss, because as it turns out, the combined solution is much faster and easier to implement. For example, we can take a look. I have it here in the classifier. So this is the whole backward method for like combined. But if we take a look, for example, on the backward method for the softmax activation, wait, what's happening? What's happening? Let's be. Yes. So for example, if we have the backward method, so this is the backward method only for the softmax, right? And well, the backward method for, where is it? For the category cross entropy loss is much simpler, but still. And this is the combined version. Pretty easy. It's just, well, two loops, but it's, well, it could be done in a one loop, I think. And right now, what is left? I mean, to finish this chapter, there are just two things left. The first one is I still want to do the same as here and calculate how faster it is. I'm just curious to compare it with the Python example. The only thing that now they creating the softmax output and the class targets once, and then they loop in the lambda. The loop in the call of the function. The first function calculates the combined version, and the second one calculates that separately. And I'm not sure that it's makes sense, because like, okay, on the first iteration you will actually have the real computation, but on the second and go further you will, okay, I had to interrupt because I had a delivery guy, and you know how delivery people knows the most inconvenient time for you to make the delivery? Yeah, that was the case for me right now. So what I've been telling is, for example, on the first iteration, you will have the real computation, like all of the real computation, but it's, how to say it? You will run the same function over and over like 10k times, and I'm pretty sure that, the results of this computation will be somehow cached on the CPU level. So, well, maybe it's still worth to do it like this, but I think I'm not sure it's far away from just run it one time and compare the results. I don't know, maybe in the Python that's different, but I assume that, well, I'm pretty sure that the Python uses some vector optimized computation libraries to make it faster. Yeah, but okay. The another way will be to randomize creation of this array every time, and then it will have to do the computations more or less, okay, but I think that's fine. So what I'm going to do, I want to test the same couple of times, and see the difference. So for example, I don't need this, I don't need this, this and this. So what I'm going to do, start 1 equals to time now, I think. Yes, this is in the time function. Test backpropagate. Then what we're going to do, we're going to do less than k times. Why not using the I itself rather than doing just too many times, and then we calculating the result, which is time, or the time now sub, right? Returns the duration t minus u. So this is the start 1. Why do you like? Can't use time and sub. What don't you want? Oh, it returns time and okay. Duration 1. Yes. This is the first one. Okay, this is, well, this is the second. This is the second one, right? But it's not. That's 2, that's 2. And they're not used. So we're assuming that the second one will take longer, which means that we're taking the second duration and dividing it by the first one, and should use time since instead of. Okay, what is since? This one. Since returns the time elapsed since it's a shorthand for. Oh, so time out. No. So it will be time since. Oh, since like this. Start 2. Right? Okay. Yeah, that's faster. Well, okay, it means that we can run. Uh, 5 seconds. Can I take some absolute value? Nano. Seconds and seconds it is. Second, this one. Okay. That's interesting. Did I do something wrong? It looks like the... Oh no. Okay. We can see that it takes much more time to process it, which is kind of same as here, but the results are pretty different. So I assume, well, it's just not enough iterations, and I would still, you know, do the randomization to have real calculations like every single time. Okay, I think that's fine. I mean, we still see that it's faster. And another thing that we go into, okay, I tested. Another thing that I'm going to change is, well, change the run model. The first one is, so instead of having this activation, well, these two activations will have one. Let's take a look that it works. Okay, this is the backward path, and calculating the gradient separately is about 7 times slow. Well, let's take the code of the model, initialize the new class of combined accuracy and loss classes object. So here, instead of this activation, we're going to have, instead of the previous activation to and loss function, we'll replace with, then replace the forward path calls with this object with the following path calls on the new one. Then instead of the previous, okay, we call it loss activation, right? And it's, where is it, classifier, this one. Then instead of two functions, like instead of two forwards, we're going to have forward the same that the activation 2 has, which is dense to output with target classes, right? So we don't need this and we don't need this. And the loss value, right? So loss value we will take from here. We don't need this. And the accuracy we will take from loss activation. Loss activation output. Loss activation. So then we should have the loss value and the accuracy. And in the backward path, that will be loss activation backward. We will take the activation. Oh no, dense to output. Dense to output and target classes, and that's it, right? Yes. Okay, we have some loss value, we have some accuracy. Okay, so I changed this one, and finally add the backward step and printing the gradients. So we have the So we have the loss activation backward, then we have this dense to backwards, which takes the loss activation, the inputs. Then we have activation 1 backwards, which takes the dense 2, the inputs, right? The inputs. Layer. Okay, we the weights. DBiases, Deviation 1, and the last one is dance 1 backwards, which takes the activation 1, the inputs, right? So then we can print what we can print. We can print the gradients. That will be for that. Then one weights. Oh, D weights. D weights. What do I mean? Can oh. Okay. DBiases, the first one, and second and second. Oh, wish me luck. Okay. The inputs, layer go. But it didn't change. Right. That's it. Okay. What a strange formatting. Okay. Maybe it's just a very small numbers, I don't know. Well, I mean, it definitely calculates something, so that should be okay. Oh, code. I'm just taking let's see the output of the cards. We have the loss, we have the weights. I'm just checking. It takes from the activation. This this one, the previous one, and it takes the output. Understand why it takes. Well, yeah. Loss activation output and okay, yeah, that's me being stupid. Loss activation, that should be the case. Okay, it's still some values, but oh, I think this is such big row because of the biases, right? They one-dimensional. Yeah. No, wait, but then why we have... Why I have such a big... Yeah, the biases should be very small. Why it's so big? Maybe I created it too big. Details, print, themes, dance one, themes. It's 300, but it should be 1 to 3. So, and it actually calculates the 3 values, but so there is, we calculate the DBiases in where? In the backward method, right? Biases row. But that's incorrect, right? Okay, let's try again. Yes, that looks like something. So what I have the loss value, I have the accuracy, I have some weights, some of them are pretty zero for the first layer, and well, weights for the first layer and bias for the first layer, and same we have for the second layer. So it looks like, and yeah, it's actually interesting how the first layer always have 0 value somewhere. But yeah, so it finally works. I will remove for this initialization, I think here. This one, right. Okay. That's much better. Full cut up this point. 1, 2, 3, 4, 5, 6. 6 pages of the code. So there are changing some mistakes. Updated. Oh, they using n inputs and neurons. Yeah, I would say it's easier. The important part is not the comment, which is also missed, but the missing n underscore in variable names, which we have added everywhere else. Okay. Yeah, so basically some changes. Okay, I'm checking the... Okay, I will start for the next chapter. Okay, once we have calculated the gradient, we can use this information to adjust weights and biases to decrease the measure of loss. I mean, that was the whole point, to have the d-weights and d-biases to actually make changes. In previous example, we showed how we could successfully decrease a neuron's activation functions ReLU output in this manner. Recall that we subtracted a fraction of the gradient for each weight and bias parameter, while very rudimentarily this is still a commonly used optimizer called stochastic gradient descent. As you will soon discover, most optimizers are just variations of stochastic gradient descent. Well, they're not decreasing it here, just printing. I don't see any actual changes in the weights, but okay. Stochastic gradient descent. There are some naming conventions with the optimizers that can be confusing, so let's walk through those first. You might hear the following: stochastic gradient descent, vanilla gradient descent, GD, or batch gradient descent, or BGD, or mini batch gradient descent. The first name, stochastic gradient descent, historically refers to an optimizer that fits a single sample at a time. Single sample. It's not our case, right? The second optimizer, batch gradient descent, is an optimizer used to fit a whole dataset at once. The last optimizer, mini batch gradient descent, is used to fit slices of the data set, which we could call batches in our context. Naming convention can be confusing here for multiple reasons. First, in the context of deep learning and this book, we call slices of data batches, where historically the term to refer to slices of the data in the context of stochastic gradient descent was mini batches. In our context, it does not matter if the batch contains a single sample, a slice of the dataset, or full dataset as a batch of the data. Additionally, with the current code where fitting the full dataset, following this naming convention, we would use batch gradient descent. In the future chapter, we'll introduce data slices of batches, and we should start by using mini batch gradient descent optimizer. That said, current naming trends and conventions with stochastic gradient descent in use with deep learning today have merged and normalized all of those variants to the point where we think of stochastic gradient descent optimizer as one that assumes a batch of data, whatever the batch happens to be a single sample, every sample in a dataset, or some subset. I mean, you can represent anything like as a slice. So slice could be one sample, a slice could be the whole pie, like, you know, it's just one tiny slice of pizza and it's the whole pizza. Or you can use a batch, like partially. In the case of stochastic gradient descent, we choose a learning rate, such as 1. We then subtract the learning rate multiplied by the parameter gradients from the actual parameters. If our learning rate is 1, then we're subtracting the exact amount of the gradients from our parameters. We're going to start with 1 to see the result, but we'll be diving more into the learning rate shortly. Let's create an SGD optimizer class code. The initialization method will take a hyperparameters starting with the learning rate for now, storing them in class properties. The update params method, given a layer object, performs the most basic optimization the same way that we performed it in the previous chapter. It multiplies the gradients stored in the layers by the negated learning rate and as the result of the layers parameters. It seems that in the previous chapter we performed SGD optimization without node. The full class would be, okay, so we have the learning rate and we have the function update params, which takes the, okay, the users we need to create. Okay, let's create it. Where to put it? Optimizer and SGD, right? Package optimizer. Well, in our case, it won't be class, it will be a struct. So let's type optimizer SGD. We have it as struct, and we'll have the learning rate. Oh no, learning rate. Not struct as float 64 equal to 1. I cannot have it. Oh, wait, I don't believe it. Struct. Wait. No. But I cannot open it from here. Oh. Right. Doc explains. Okay, types. No. Function guides. Okay. Struct. Okay. Okay. We have a learning rate. New SGD. Right. And it returns the optimizer. And we return no. Won't understand it. Okay. Optimizer learning rate 1.0. So far so good. Then I need import of main layer. Why? Because we're going to have the optimizer optimizer is GG, and it will be update params. And update params takes the layer of, well, it takes the layer and yes. So what we should do, we need to change, for example, we have a layer, we have weights, right? Okay, my cat wants to take a part in this coding series. No, don't try to use the coffee. Yeah. Can I finish? I need 5 to 10 minutes. Huh? What do you think? Okay. We'll see if we... Okay. Let's try. Okay, so the first thing we need to actually make a copy. I've been thinking right now. And I need to make a copy of first thing first, we need to create a copy of the DWeights and DBiases, because we're going to change them first and then use the method to subtract one matrix from another. So what we're going to do, so we're creating the DWeights, right? And that will be dense copy of layer DWeights, right? Same, we have DBiases and DBiases. So we've copied them. Then DWeights, we need to apply, right? Apply. Function this one and DWeights, right? And what we should return b multiplied by -1 multiplied by optimizer learning rate. Same I have for DBiases. So this is, I'm implementing for this part. This is what I have. Then we need to actually update stuff in the layer, right? So we have, for example, DWeights, and we need to use sub subtracts the matrix B from matrix A, B from matrix A. So it means that we're going to use weights and we're going to subtract DWeights. And same here. And that should be our optimizer. Okay. Okay, let's call it. I think this is, we should have it here, so it's optimizer. Optimizer equals to optimizer dot, oh no, new SDG. Okay, I will use O. Then what we do, we take in the update params and we pass first layer and we pass the second layer, and it should work. Okay. Recall that the layer object contains its parameter range and byte, and also at the stages gradient that is calculated during the backpropagation. We start this in layers properties so that the optimizer can make use of them. I mean, I'm not sure at this point why we even need a separate class. We can, we can have a method for the layer class that do the same, because all the things, what actually the update parameter, the only thing that it's a gradient rate, but we can do the opposite. We can pass the gradient rate into the function and for the layer. But I mean, okay, let's do it like this. Okay, we start. Let's make a 1/64 densely connected neural network, one hidden layer with 64 neurons, and use the same dataset as before. One hidden layer, this is one hidden layer, this is 64 output values. Activation, loss function, create the second dense layer with the, yeah, but I would call it output layer or something like this, but okay, dense layer 2. Then the next step is to create the optimizer, then perform a forward pass. Next, we do our backward path, which is called backpropagation. This is everything we need to train our model. And then we go for the epochs. Okay, and this is, oh no, that's not the end of the okay, let me check the timing. Okay, I will stop for today and I'll continue tomorrow. I will start from this another network and from the epochs, and then we'll go to see how I think we're going to take a look how we're going to pick up the proper learning rate instead of just hard coding the one. Okay, thank you for watching, and I see you tomorrow. Bye bye.